my pleasure today to talk about the plasma and electro-energetic physics portfolio. Next slide. Plasmas, what do? You take a solid, you add energy, you get a liquid, you add energy to that, you get a gas, add energy to that, you get a plasma. And now you've got an energy-dense object, which has got a number of unique parameters. First of all, it's charged, so it has long-range forces, and that creates a whole slew of new physics. Similarly, it's energy-dense, and therefore there's lots of ways for that energy to go, sometimes good, sometimes wrong, and so we learn how to control that. The challenge with plasmas is that once you've made an energy-dense object, you can have lots of options of an energy-dense object. So if you look at, this is the parameter space for plasma physics, temperature going from 10 to the minus 5 eV to 10 to the 10th. Similarly, densities going from 1 to 10 to the 30th. Oh, got cut off right there. So you see that we have a huge range of physics, okay? All of which is described by plasma physics, going from white dwarf stars, black hole accretion disks, partially ionized plasmas, flames, things like that, okay? This is the entire plasma physics universe. The gray boxes show the investment that's occurring by other partners in the federal government. Typically, the Department of Energy is the big second player in this. However, I've added some boxes. The red boxes in red are part of my portfolio. The blue boxes are additional plasma physics investments that are done in conjunction with other portfolios. We talk a lot. We'll touch on the physics of that as we go forward. So with that, in particular, I'm going to talk about high-powered microwaves, which lives up in here in the relativistic plasma physics energies. These are electron beams. They're non-neutral plasmas, which has their own set of physics associated with it. And then similarly, I will also talk about non-equilibrium plasma physics that are neutral, where you have electrons and ions that present overall charge neutrality. That's in this box right here. Similarly, we also will talk a little bit about pulse power. That's the energy that we use to drive these systems. So you see these red boxes, that's what we're going to talk about today. And with that, we'll go to the next slide. The real question is, if you've got a universe like that, how do you choose what to invest in? These are some areas that I choose to invest in. Again, it's fundamental science to affect Air Force needs. Several of these are part of the tech horizons, in particular the electronic attack, non-lethal weaponry, electronic warfare, high-powered microwaves, directed energy devices. Similarly, there are also needs that are pointed out in Tech Horizon for enhanced combustion, enhanced energy efficiency. Plasmas touch on that. You can see some pictures of active denial systems. You can actually look this up on the Discovery Channel. And similarly, you can also see interesting pictures, interesting plasmas with plasma combustion devices. One thing to note is there's a joke. Plasma physicists were seduced by neon signs, so all we're looking for is really pretty colors. That's ultimately what we're doing here. But you see, there's actually a whole slew of things. I'll also talk a little bit today about how high-powered plasmas affect metamaterials, which is some direction that we get from ASD R&E. And finally, the other thing that is a driver on what we invest in is the scientific community at large. Plasma physics has a number of reports from the National Research Council. We try and keep track of that, as well as any new and exciting developments in the field. Next slide. So, why is it hard? These are Maxwell's equations, and what's different about the way you sometimes see it is that the sources are there, and the sources are important. Plasma physics is energy dense. That means that we have to solve all of the dynamical equations, the AC equations, if you will. There are sizable DC fields associated with the plasma. Can't ignore them. Similarly, the plasma is made up of charged particles. They move around in response to those electric and magnetic fields. And similarly, those sources then create the electric and magnetic fields. So you have to solve them all. And if that wasn't bad enough, you also have to solve the materials things, because oftentimes the way we make a plasma is we stick an electrode in that. So there's a new effort that involves several program managers, myself, Mitat Birkin, and Ali Sayer on materials and processes far from equilibrium. You'll hear that theme of the physics associated with the electrode in addition to the physics associated with the plasma. It's multi-scale, multi-physics. So long story short, we have to solve all of these. It's hard. That's why it's its own field. It's 7-dimensional. There's a dimension of time, 3 dimensions of space. We also have to track 3 dimensions of velocity, if you will. It's electrodynamic and electrostatic. You have to do relativistic statistical mechanics. You have to do self fields and AC fields. Oh, by the way, you have to do quantum mechanics to get the electrons coming from the electrode into the plasma. Long story short, it's hard. This is why plasma physics are notorious know-it-alls. Okay? The other way you can do this, though, is that you collaborate with all your great friends and colleagues at AFOSR. So, next slide. Another way to say that it's hard is, again, I'm hitting this regularly. These are energy-dense structures. This is 2 nuclear power plants from Wikipedia, source of all knowledge. Similar, they're 700 megawatts. There are 2 of them. They're on an island. Okay? Imagine all of that power being stuck in something roughly a meter cubed. Okay? There's the standard issue ruler. This is a magnetron. We'll talk about that in some detail. That energy density means there's lots of ways, lots of pathways for the physics to evolve. We want to track that. And in particular, what we want to do is track this so-called non-equilibrium phase, where as we apply power, the structure heats up. And again, they're long-range forces. And during this so-called turbulent quasi-equilibrium, it's quasi-equilibrium in the sense that the power is not changing, but you see that the entropy is changing. And as that happens, plasmas self-organize. We want to track that structure because that's determining where the energy goes. One of the ways that shows up is that if you fire high-powered microwaves into the air, you get a breakdown structure. Initially, that appears as a blob, but it actually self-organizes into these structures, which actually have many of the features of a metamaterial, except that you've made it with a plasma. Okay? The other thing that makes it hard is that there are lots of time scales. We're going from femto to picoseconds in terms of electrons coming out of materials. They transport on the scale of nanoseconds. These devices run from milliseconds to CW. Similarly, we're going from nanometer type structures, pointy tips, to devices that are meters long. So there's a tyranny of scales. All of this is what we're trying to do to understand and control where the energy goes so we can do useful work. Next slide. So first topic of today in my portfolio is high-powered microwaves. The device up here is a magnetron. It's exactly like what's in your microwave oven, except that it does 1 billion watts. We used to joke that we're going to send microwaves downstream to help the troops microwave popcorn. They just hold the popcorn up and we'll blast it. Again, it's exactly like your microwave oven in the sense, if you can see, there are spokes that appear on this structure. And those spokes are electrons that are emitted from the cathode. You apply a voltage between the cathode and the anode. That rips out and it self-organizes into this spoke structure. It's exactly like an electromagnetic whistle, except that the electrons are performing the role of your breath on a whistle, and you're generating electromagnetic waves instead of sound waves. Again, 1 billion watts. This is an old field. It's arguable that with the invention of radar, it was highly critical that it played a role all the way back in World War II. Of course, it actually predates that. One way to show that is power times frequency squared, which is energy density. If you want to chug through the math afterwards, we'll sit down and do it. But since 1930, high-powered microwaves and vacuum electronics have been doubling in the energy density that's in a source every 26 months. So we're not quite Moore's law, but we've been doing it longer, I'd like to say. And second of all, it's still fairly impressive. One of the ways that we've been able to keep doing that is the recent advent of codes like Icepick, funded by AFOSR, our colleague Fariba Farouk, that do 3D high-fidelity parallel modeling of these plasma systems. Okay? To show you that what capability you have in that, this is an actual simulation of this device. The red plots are Icepick simulations. It's a true prediction 6 months before they cut metal. The blue dots are the experimental performance. You see, we have at some level of fidelity for devices that are relatively low frequency, enormous capability to predict and model these things. Okay? This is a device that's consistent with a directed energy technology. The challenge, however, is by getting so good at making these microwaves, one of the big new developments is that we can break down the air. We can send enough microwaves out into the air that the plasma forms in the air and stops the propagation of the microwaves, which is shown here. Again, these are 3 shots. The gray curves are open shutter. You can see that the formation of plasma is reproducible. This is in atmospheric air. And you can see that as a function of time, 10 nanoseconds, there's a plasma breakdown there. At 152 nanoseconds, it's propagated out there. A microsecond, and it's actually moving towards the source. This physics is similarly non-equilibrium in the nature that we were talking about before. You can see there's structures on this. It's also stopping the microwaves from propagating. So we regularly reach the limit of air breakdown. So the question is, what's the next 6.1 basic challenge associated with the high-powered microwave technology, given that we can break things down? This effort is actually funded in a counter-directed energy program. So there's lots of cool physics there, and we're investing in that. But let's talk about what to do with the sources going forward. Next slide. Here's a grand challenge. Okay? Everything I've been talking about to date are oscillators. okay, high-powered oscillators. High power almost inherently means you're going nonlinear. You're trying to get as much energy out of this as you can. However, electronic warfare, radar, communication systems, things like that all depend on having control of the waveform. That is to say, we want to linearly amplify the waveform to high powers to do interesting things. Linear means amplification, high power means nonlinear. Doing both is a grand challenge. To show you what I mean by this, consider the Haystack radar. It's a state-of-the-art radar, 94 gigahertz, based on a gyrotron-like device, okay? Does 80 kilowatts peak power, 10 kilowatts average, but it has 700 megahertz of instantaneous bandwidth. You can do really cool signals, okay? In contrast, consider the ITER system, 110 gigahertz. In my world, that's roughly the same frequency. It's the same technology, also a gyrotron. Does a megawatt and does a megawatt CW, 15-second pulses, okay? So long pulse, high energy, high power, however, has 1 megahertz of bandwidth, and that's on a good day, okay? The interesting thing is these are both gyrotrons, and no one understands the space in between them. We don't know how much power we can amplify and still retain a linear signal. So that's a fundamental challenge, and the big reason why is as we add more and more power, we add more and more so-called space charge, more and more plasma physics, and that results in the amplifier becoming an oscillator. Next slide. One way to tackle this is to try and make inherently single-mode devices. We've got two structures here that came from our friends. One is at Strathclyde, funded by EORD. The other one, Rick Temkin at MIT. These are either photonic band gap structures, metamaterial structures. We can talk about offline my particular views on the lingo on that, but make a long story short, these are structures that inherently have one mode. Okay? We engineer the structure given the interesting capabilities of a metamaterial to create a single mode structure. Okay? I've showed this before. You can see that in the case on the left, you get one mode. In the case on the right, it's really very interesting, and this structure looks very similar to what you'd get if you just had a can. However, if you go up in frequency, because of this photonic bandgap structure, the energy just leaks out. The mode doesn't exist. So metamaterials are offering us a capability to engineer the electrons, or excuse me, the electromagnetics of the problem in new and interesting ways. However, what happens when we stick a high-powered beam in that? Next slide. This is an initial effort being performed by our friends out at RD. It's Don Schiffler's group, if you guys know that, and I believe Don is in the room. There he is, so he can correct all my lies as we go forward. This is an initial effort to look at what happens when you take a standard metamaterial, and here we're using Dave Smith's structure from Duke, which is a double negative material. It's a split ring oscillator. It's two rings together that have a resonant mode, together with a wire that actually produces a double negative device. That is, the epsilon and the mu's are less than 0. Novel physics, okay? They actually take that structure and then they perform theory trying to understand how that's impacted by the beam. They do this in two ways. One is so-called Pierce theory, which is shown in the upper right-hand corner. This is frequency versus wave number, and you see the black curve? That's the electromagnetic properties of that structure. Now, when you want to make a high-powered microwave device, you want to take energy from a beam and have that resonate with the structure. So the orange line is what you get with the beam, and where you get an intersection is where you get strong interactions where you generate microwaves, okay? This is what we want to look at both theoretically with the Pierce diagram and in the Icepick code, okay? The blue curve, by the way, is the light line. That's the speed of light traveling in vacuum. Okay, but really we're going to focus on the black curve and the orange curve. Next slide. Well, you know, it's not an AFOSR talk unless it has a movie. This is a structure of an electron beam going through a metamaterial, and you see that the beam is highly bunched. Bunches of electrons, and also that there are very high fields on the actual electron structure. So it's doing its job, it's making microwaves. But what can we learn about this? Top curve is what you get if you just fire in 1 amp. It's basically identical to what you had before. Look where the black curve intersects the blue curve, okay? It's nice and clean. You get one intersection. That's what we want, right? We want one mode to get amplification, and we see a nice, if we look at the power versus frequency below this, you see a nice clean spectrum. However, as we turn that up, we go to higher power, we add more plasma physics, look, the structure deforms. See that there's a bending right there, and a new circle appears right there. Okay? This is so-called beam loading. It happens in standard microwave tubes. But what happens is that it causes the tube to oscillate. Okay? There's a current at which that happens. Lo and behold, if you look down at the frequency plot below, you see that there's a broadening of this pulse, which is consistent with the beam deforming the properties of the electromagnetic structure, and similarly with creating a new structure right there. When that happens, this beam loading, it's no longer an amplifier, it's an oscillator. Okay? So this is the first efforts on looking at how to do beam loading in the context of metamaterials. Okay? Now, it seems like this is a sad note to stop on, but of course there's a lot of space between 1 amp and 10 kiloamps, so I've got some room to maneuver in there, as do my PIs. And similarly, already, if you look at the far, corner, this is the gain in dB per centimeter versus current. You see that we're actually nearly a factor of 2 over the state of the art. This is a computational study. We still need to build it. But the really interesting thing, and if you remember Don Hearn's talk yesterday, we actually now have the capability to model and engineer the structure such that we prevent this. So it's an important first step. It's very exciting. Next slide. Now, if you go back one, I'm sorry. Second thing I'm going to talk about with high-powered microwaves, and this shows how the materials and the plasma need to interact together. See, there's a thin beam going through the structure. Next slide. One way to do that is to actually make little lightning rods. Again, this is still work at RD, Don Schiffler's group, specifically Wilkin Tang, who was in my portfolio as a graduate student, now at the lab. And he's looking at the following physics. Imagine you apply a high voltage on this structure. What you end up getting is, on the electrode side, there's a population of electrons that are in the material. As you apply a high field to that, you actually you deform the barrier between the vacuum and the structure, and that allows electrons to tunnel out. It's called field emission. Okay? This has been known for a long time. It requires very high fields, 1,000 volts per meter. What's interesting, however, is that the pointiness helps, field enhancements associated with that. And similarly, there are material properties associated with certain materials like carbon, which put atomically sharp pieces on the structure, which help create these high fields. Okay? So the real question, however, is we've never been able to separate, despite the fact that we've been looking at this for a very long time, the effect of material and the effect of geometry. This is a study that specifically isolates that. Next slide. These are Icepick simulations, and you can see that there's field enhancement associated with this. So we're actually using the simulations of the experimental structure I just showed to capture the field enhancement. And similarly, we're doing some analytic theory. The technique was developed by Y.Y. Lau at the University of Michigan, also in our portfolio, and then being applied by Wilkin to understand the conformal mapping for the field enhancement to isolate all the effects of geometry. Everything that's left is materials. Okay? What we then do is we actually build lots of these structures and see what we can figure out through statistical processes to what piece of its materials versus what piece of its geometry. And if you do all this, next slide. This is a comparison of what you get when you do all that work very carefully and use Icepick, a simulation tool, versus experimental data. What we've been striving for in all of this is predictive capability. Be able to simulate the device before we build it. See, if you're very careful, you actually can develop that predictive capability even on the field emission. Again, this is brand new. Typically what's done on the field emission front is you twiddle knobs until you get the data right. This is a true predictive capability and a great enhancement to how to design the device. Next slide. Okay, changing topics. Up to this point, we've really only been dealing with electrons. Now we're going to start talking about electrons and ions, or so-called neutral plasma. The left-hand side is what you normally get when you have a so-called etching device. So every computer in this room, every computer chip, your cell phone, your computers, things like that, all were etched with plasmas. That's how you actually make the computer chip. It's a huge industrial process. You all can buy me lunch afterwards if you like your smartphones. But the way they do that is, again, at relatively low pressure, they have a large electrode. It's a large volume, low pressure, 10 to the minus 5 torr, and it's non-thermal. Okay? It's also so-called collisionless because of that low density. The problem is that most of the time where the Air Force wants to operate, the enemy will not let us put a vacuum chamber around the structure, right? We want something that absolutely can operate in the air, hence Air Force. So a really exciting innovation that's occurred in the past 10 years is the so-called microplasma, which is shown on the right. We'll talk about it in some detail, but there's gas flowing down a tube. The electrodes are actually this structure, and the rest of the air ground is way up there, okay? And you get a dot of plasma. So what's interesting about that? It's operating at atmospheric pressure. It's still non-thermal, which is how we get all the interesting chemistry associated with the situation on the left. And it's collisional, but it doesn't transition to an arc. So I've been talking earlier about non-equilibrium. There's an instability that takes a plasma to an arc. When you go to an arc, you start dumping lots of heat. This, despite being at atmospheric pressure, does not do the arc transition. Why is that? We want to understand that, and then what can we do with that in the context of what can help the Air Force. Next slide. Again, these are just some details about the microplasma. They're tiny, okay, 100 microns. They're cold for the gas, but all the energy is in the electrons, which means we're able to modify the chemistry. Okay, we're going to start talking about chemistry. They're extremely high electron densities for atmospheric pressure, at least in a stable way. There are other ways to make large electron densities, again, stable at high pressure. And this goes to, this is an area that was the science really was screaming that we needed to invest in it. The National Research Council points out that this is the most exciting development in plasma physics in a number of years. Next slide. Yep, offers some key advantages for nano manufacturing, which is one of the examples that we're going to talk about, okay? Before I move on, though, I'd like to mention that you're looking at that one dot going, how much good can I do with that? You can actually build arrays of them, okay? A transition that I didn't have time to put into the slides, but the folks said that I could talk about it, is you can now make arrays of those, and they're doing things like making ozone. Ozone is an important way to purify water. Fairfax County has 2 block-sized facilities that make ozone for Fairfax County. Our friends in an STTR have a truck-sized device that's making as much ozone, suitable for being used in forward deployed bases and things like that. So again, you can do arrays of these. That's a transition. Next slide. Real question is, how are these things working? Why are they not transitioning to the arc instability? Well, there are those electrodes again. It's the same physics that we were talking about in the field emission earlier. The interesting thing in this case is, remember, we have a neutral plasma, so there are ions in it. So again, we're deforming the barrier between the material and the plasma, which is shown here. And if you sort of drew a straight line in your mind, that looks like the plots we showed earlier, but now we've got an ion in here, which is creating a well. This allows both field emission exactly like we saw before, and similarly, there's a second process where the ion crashes into the material, raises electrons up, and the electrons come out. So again, we're talking about materials and processes far from equilibrium. The reason the microplasma works is it's coupling together 2 sets of multiphysics, the material physics and the plasma physics. And when you do that, if you plot voltage to get a breakdown versus electrode spacing, in the big world, you get something called Paschen's curve, which does this. It's a U shape. But when you bring these electrodes in and you strongly couple to the electrodes, lo and behold, this bends down, okay? Our PI, David Goh at Notre Dame, has worked out the theory for this, and we're comparing both theory and experiment, so nice fit, concluding these processes. And the other thing to point out is that throughout my career, the real problem with plasmas is that you need to get a lot of energy to make them. I might have mentioned that they're energy-dense objects. They're still energy-dense, but it's energy density here. And so what we can do is, as this voltage goes low, we can do more and more of them. It's easier to package it. It's easier to use it in Air Force applications. It's a revolutionary breakthrough for getting the benefits of plasma onto mobile platforms. Next slide. Even if you don't want to go mobile, there's new and interesting things that you can do, and this is the work of Sankaran at Case Western Reserve. Both the last 2 slides are yips of mine. The great thing about microplasma, it's filled with young people who are excited and gung-ho. This is a continuous flow microchemical reactor based on microplasmas. That little dot that you saw earlier would be right there. It's between a cathode and an anode. You control the gas flowing in, you break things down, and by changing the gap spacing, the voltage between it, and the flow gas that's going in, you have control over chemistry and resonance time. okay? When you do that, you can make very interesting and, more importantly, very precise amounts of nanoparticles. So next slide. To show you as an example, this is iron that's attached to an organic. That's the fill gas, goes into the plasma and breaks up, leaving the iron alone, and then the iron coalesces due to the plasma physics onto microparticle, nanoparticle type objects, okay? Looking back at this slide, by changing the various parameters of the operation, you see that you get a very narrow range of sizes in the nanoparticles. So we have high control over the size of the nanoparticles. Also, you can do things like put in 2 sets of metals and do bimetallics, which are interesting to the RW community as a potential energetic material. The transition associated with this is the fact that our friends at RX are already using this to do safety studies, because the big problem with doing safety studies is that you want to have particles that are all basically the same size to make sure the filter is working, okay? So this has already been used in the RX to do health and safety associated with nanoparticles, which is a big question how we're going to use that in the field for health and safety. Again, the control over the details of making the nanoparticles allows us to have very fine control, not only over the properties, but over the sizes. The other interesting thing, and this is why I love 6.1 work, is imagine that instead of firing in iron, we fire in just carbon. Lo and behold, they're making diamond films at room temperature with this. Same process, by varying the flow gas, the amount of power that you're dumping in, the residence time, you can actually make diamond films made out of carbon nanoparticles. This is a micro-Raman spectroscopy, which shows you the signature of the diamond. What's exciting about this is that in the 1980s, it was posited that diamond is actually more stable at the nanoscale. You don't need all the pressure. You don't need all the temperature to make diamond. So we're actually changing the chemistry, able to operate at generating diamond at room temperature. And again, it's just a very exciting thing. What I love about 6.1, there's really cool plasma physics. There's really cool material science. And guess what? People are using it in the field to help save lives. So it's just great. Next slide. Okay. Everything that we were talking about up to that point was small microplasmas. Here, we're going to talk about fast. So this is a transient plasma. The name is exactly what it means. You apply voltage for a very short period of time. And new and interesting things happen. Today we're going to be talking about ignition. In particular, if you do a spark, which is 15 kV pulse, 10 microseconds is the right-hand side. You get an arc, which you can see up there, okay? And that ignites a fuel that has an expanding as a function of time. If you do this with actually a little less energy, but only 12 nanoseconds, you get all this extra structure. You get so-called streamers, lots of different physics. It never transitions to an arc simply because it doesn't have time. It's non-equilibrium. An arc is a collisional instability. Because of that, lo and behold, the flame speed associated with this is 15% faster. So we've changed how the flame is going, and again, that's mainly because we're not forming an arc. We're depositing energy all around the structure. But there's some other interesting things when you do this. You might think it's just a cool spark plug, but maybe you can do something else with it. Next slide. Lo and behold, the plasma lights off faster, okay? So the red is the transient plasma ignition, the black is the spark. We see about the same pressure because that's the amount of energy that's stored in the chemistry, okay? But remember, we're talking about, the scale is milliseconds. We're talking about nanoseconds or microseconds. All the plasma physics is way over here, okay? We're actually changing the details of the neutral chemistry coming into it. And lo and behold, it's igniting faster. So reduction in ignition delay, that's important for hypersonics, both pulse detonation engines and scramjets. Igniting a hypersonic device has been compared to trying to light a cigarette in a hurricane. It's hard, keeps blowing out. The plasma physics is actually depositing all the energy before anything has any time to move. That changes the chemistry and you get this speed up, okay? Second thing that in both in aerospace systems and in internal combustion engines, it lets you run leaner, allows you to ignite a wider range of fuels, allows you to ignite higher mass flow rates, And there's some evidence that it's a much more complete combustion. There's a lot less soot coming out of it. So it's also helping efficiency. Next slide. Okay. This is all that work on the transient plasma ignition was at USC. And we're going to switch gears here now to the devices that power these. So it's pulse power. You take power and you add it over a long period of time, and then you discharge it very quickly. The energy is roughly constant, but you get high power. These combustion systems are really dependent. You can't separate the pulse power from the plasma. So we also fund the compact pulse power work at USC. I've been told this is absolutely to scale a standard issue USC graduate student. And you can see how the device has shrunk over time. Perhaps more importantly is the change in the waveform. It's getting sharper. And that sharpness is important to maintaining this non-equilibrium. What's exciting about this, if you look at the large view, is that even though we're doing fundamental work on the pulse power, and we'll talk about what that is in a second, these systems are being used both at RZ and at the Naval Postgraduate School to fire off their hypersonic systems. So this is actually a thing that I think is a theme throughout what I'm talking about. There's very tight coupling between the service labs and people in the portfolio. Okay? We try and put our badges away and go to work. Okay? Next slide. What we're doing to get these very sharp pulses is we're so-called nonlinear shock lines. You apply a nanosecond, and the pulse travels through this shock line, and because of the nonlinear properties of that, the shock line actually sharpens. It actually peaks up. It's the equations are identical to a wave breaking. Okay. In particular, what USC is really looking at is both ferroelectric, ferromagnetic, and ferrimagnetic materials. And in particular, they're trying to find a way to take all this energy and power we were talking about earlier. These types of materials have been known for a while. Getting them to run at a megawatt per centimeter, over centimeter cubed energy densities without exploding is the challenge. So it's tightly tying the electrical engineering, the material science, and the plasma physics together. So next slide. Similarly, so you don't think that we might be ignoring the electric side of the house, I'd like to close with one more thing about, again, pulse power, and this is nonlinear dielectric science being done by Susan Hydra at RD with support from Pacific Northwest National Lab. In particular, here what we're trying to do is instead of storing lots of energy, we're trying to send in a DC input pulse. And because of the nonlinear interaction, it actually turns it directly into an RF pulse. So we're removing the electron beam from the earlier part of the talk. It's a much more compact system. Probably can't go to gigawatts, but it probably can go to megawatts. In particular, the challenge associated with this is that if you have low loss, you get lots of RF. If you have high loss, it dies. So we're actually looking at new novel materials. This is being done again at RD and Pacific Northwest with the CQuest DFT code coupled very tightly to experimental efforts at Kirtland. And the interesting thing is the density of states associated with these devices really depends on how you terminate the structure. So this is barium titanate, which is one of our candidate materials. But how you actually terminate it, whether you terminate it with the barium side or the titanate side, the oxygen side, that actually determines how it connects to the electrode. And again, we're back to materials and processes far from equilibrium. So you need to do all of that. And this sort of work is actually leading to both new materials and new manufacturing techniques. So it's state-of-the-art modeling of materials, ab initio modeling, tied to experiment, trying to make low-loss material. Next slide. So this is almost my get-off-the-stage chart. Again, I'm, of course, biased, but I think we're the preeminent 6-1 organization in plasma physics, especially for high-powered electromagnetic sources. We have a laundry list of accolades for the portfolio. I'd just like to point out two. It's always nice when our senior PIs are recognized, but our graduate students in this portfolio are being recognized. And we have a history of actually taking our friends from academia, the graduate students, and having them come to the service labs. We've got 3 new hires from this portfolio in AFRL, 2 at NRL, and we're joint, so I'll let that go. But we'll try and get them all to go to the Air Force next time around. It's very much cross-disciplinary. We work closely with everyone, NSF, ONR, ARL. In particular, we do have a joint effort with DARPA on microplasmas. And we support a 6-1 lab task with RY that works with NRL on space physics, particularly active EM fields in the ionosphere. And I'd just like to point out that plasmas can change the nature of flow in airfoils. Similarly, it changes the nature of the ionosphere in space chambers, and God willing, also the ionosphere. And similarly, it can affect, through electronic warfare and things like that, it can affect electronics, so aerospace and cyber, we're doing it all. Next slide. And with that, I've got 5 minutes for questions. If you want, I can talk over where things are going. Again, I mentioned the high-powered amplifiers, high-powered metamaterials. There's a new MURI with Dr. Nachman. He and I are doing that. A little less emphasis on the peak power oscillators. On the non-equilibrium side, we're trying to do a better job at modeling it, especially with the chemistry. I didn't have time to talk about it today, but come back next year. This is a teaser. We're going to talk about ultra-cold and strongly coupled plasmas. So if you're sitting here and you take one thing away, energy-dense objects, so next year we'll talk about how we can be ultra-cold and energy-dense at the same time. That'll be fun. That's with Dr. Kirchik, and we're holding on pulse power. So with that, I'm happy to take any questions you might have.
There's time for a few questions. Hang on.
Yeah, hi. I really thought that was a superb presentation,
Thank you.
Especially for those of us who are not experts in plasma physics. You mentioned very briefly one outside of the U.S. investment at the Strathclyde. But
Yeah.
I was wondering, had you thought at all, are there some areas of the work where you think we haven't done enough exploration, or you think we're underinvested overseas because there's some unique strengths that you'd like perhaps to see a little more exploration of?
Absolutely. So there's one particular challenge. So let me first state that microplasmas are very important in France. So we need to reach out to the French community. We traditionally have long-term relationships on directed energy with the United Kingdoms, and that's where we tend to fund our money. Asia is absolutely a great place to invest in, and also in the microplasma area. One challenge that we have is that we try very hard to not fund explicitly fusion and explicitly medical. Okay? So one of the big things I didn't talk about, the big application, especially in Asia for microplasmas, is for wound healing, bacterial cleaning, things like that. There are lots of great people, however, plasma physicists, that are doing really interesting things on engineering the electron energy distribution function to do very specific chemistry. Now, that might be biochemistry. So that's the next, I think, frontier for us to really look at overseas.
So microplasma's application to biology?
Yes. Yeah. And we can talk about that offline, but it's fascinating.